Hello and welcome to this revision session for particles in AQA A-Level Physics Paper 1, in particular quantum physics. So, if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And then this left hand side section, write down your work now and answers to the questions in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Now in the right hand side section, what you should do is write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for AQA A-Level Physics? Well, the first thing you need to do is to learn the key facts. Use revision guides, class workbook, student prep notes and the textbook to learn the key ideas of the course. Then test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. The third step is to practice. Use exam preparation books, homework books, study books, additional workbooks to answer exam questions and mark your own work. So this cycle of learn the key facts, testing yourself and practicing exam style questions are how you should be revising for AQA A-Level Physics. So what are the key facts to do with quantum physics? Well, the first thing to look at is the photoelectric effect. Now, the photoelectric effect, the threshold frequency, is the minimum frequency required for the photoelectrons to be emitted from the metal surface. How it works is that light is made from photons, and the energy of one photon is equal to E equals hf. Now, the work function is the minimum energy needed to release an electron from a metal surface, and the stopping potential is the voltage needed to stop the most energetic photoelectrons. Now, the photoelectric equation is hf is equal to the work function plus the maximum kinetic energy of the emitted photoelectron. Now, in terms of collisions with electrons with atoms, ionization is when an electron gains enough energy to leave the atom completely. Excitation is when an electron moves to a higher energy level but stays within the atom. Now, fluorescent tubes show both excitation and ionization. Now, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. When you have more collisions with electrons, what you must be aware of is line spectra. Now, that provides evidence of discrete energy levels in atoms. The photon emission equation is hf is equal to E1 minus E2, where E1 and E2 are energy levels. Now, energy released as a photon of light occurs when an electron moves from a higher to a lower energy level. For wave-particle duality, electron diffraction provides evidence that particles have wave-like properties. The photoelectric effect provides evidence that the electromagnetic waves have particle-like properties. Now, the de Broglie wavelength is lambda is equal to h over mv, where h is the Planck constant and mv is the momentum of the particle. Now, the diffraction pattern produced will widen if the momentum of the particle decreases. So, let us have a look at some questions to do with quantum physics. So the first question is, what is the photoelectric effect? So, pause the video now, then unpause the video when you want to go through your answer. The photoelectric effect is the emission of electrons from the surface of a metal when electromagnetic radiation is shined upon it. What does the photoelectric effect prove about the nature of electromagnetic radiation? So, pause the video now, then unpause the video when you want to go through your answer. The photoelectric effect proves that electromagnetic radiation must act like particles. What two effects prove that electromagnetic radiation must act like particles in the photoelectric effect? So pause the video now, then unpause the video when you want to go through your answer. The emission of photoelectrons is instantaneous, and the intensity of the radiation does not affect whether electrons are emitted or not. What does the intensity of the electromagnetic radiation affect in the photoelectric effect? So pause the video now, then unpause the video when you want to go through your answer. The intensity of the electromagnetic radiation affects the number of electrons emitted when the frequency is above the threshold frequency. What does affect whether photoelectrons are emitted? So pause the video now, then unpause the video when you want to go through your answer. The frequency of the radiation affects whether photoelectrons are emitted. What is the work function? Pause the video now, then unpause the video when you want to go through your answer. It is the minimum energy required to release an electron from the metal. What provides the energy to overcome the work function? So pause the video now, then unpause the video when you want to go through your answer. The photons provide the energy to overcome the work function. What assumption is made about the work function? Pause the video now, then unpause the video when you want to go through your answer. It is that the electrons are at the surface of the metal. What is the threshold frequency? Pause the video now, then unpause the video when you want to go through your answer. It is the frequency required to give the photons enough energy to overcome the work function. Where does any excess energy delivered by the photon above the work function go to? So pause the video now, then unpause the video when you want to go through your answer. The excess energy goes to the kinetic energy of the emitted photoelectrons. What would happen if a metal received electromagnetic radiation at the threshold frequency? So pause the video now, then unpause the video when you want to go through your answer. The photoelectrons would be emitted, but they would not be moving. What effect would increase in the frequency of the electromagnetic radiation when above the threshold frequency have on the photoelectrons? So pause the video now, then unpause the video when you want to go through your answer. The photoelectrons will be emitted travelling at a greater speed. How many photons are absorbed by an electron at one time? So pause the video now, then unpause the video when you want to go through your answer. One photon is absorbed at a time by an electron. Why do electrons in the metal have a work function? So pause the video now, then unpause the video when you want to go through your answer. Well, the work function is due to the attraction between the electrons and the positively charged ions found in the metal. What effect would increase in the intensity when above the threshold frequency have on the speed of the emitted electrons? So pause the video now, then unpause the video when you want to go through your answer. The intensity of radiation will not affect the speed, only the number of photoelectrons emitted. Why is the kinetic energy calculated in the photoelectric effect a maximum value? So pause the video now, then unpause the video when you want to go through your answer. The kinetic energy of the photoelectrons must be a maximum value as our work function is a minimum. Why are photoelectrons emitted with a range of speeds? Pause the video now, then unpause the video when you want to go through your answer. Not all electrons are at the surface of the metal, and the electrons dissipate some energy as they travel to the surface of the metal. How can the kinetic energy of emitted photoelectrons be measured practically? So pause the video now, then unpause the video when you want to go through your answer. You would place a potential difference next to the surface. This turns the kinetic energy of the electrons into electrical potential energy, and the electrons stop moving. This can be measured. On a kinetic energy frequency graph, what is the y-intercept of the straight line? Pause the video now, then unpause the video when you want to go through your answer. The y-intercept is the work function of the metal surface. On a kinetic energy frequency graph, what is the gradient of the straight line? Pause the video now, unpause the video when you want to go through your answer. The gradient is the Planck constant. On a kinetic energy frequency graph, do the gradients vary for different metals? Pause the video now, unpause the video when you want to go through your answer. All metals have the same gradient on the kinetic energy frequency graph, as the gradient is a constant value. It's the Planck constant. On a kinetic energy frequency graph, what is the x-intercept of the straight line? Pause the video now, then unpause the video when you want to go through your answer. The x-intercept is the threshold frequency. What would happen if a metal received electromagnetic radiation at the threshold frequency? Pause the video now, unpause the video when you want to go through your answer. The photoelectrons would be emitted, but they would not be moving after emission. On a kinetic energy frequency graph, why do all the straight lines have the same gradients for all metals? Pause the video now, then unpause the video when you want to go through your answer. Well, the gradient of the line is a Planck constant, and this is the same for all metals, as Planck's constant is a constant. What is the stopping potential? Pause the video now, then unpause the video and you want to go through your answer. The stopping potential is the potential difference needed to stop the fastest moving electrons travelling with kinetic energy. The next question says, what would happen to the stopping potential if the frequency of the photons is decreased? So, pause the video now, unpause the video when you want to go through your answer. Right, so the lower the frequency of the photon, the lower the kinetic energy the photon has. This gives a lower value of kinetic energy in the electrons as the work function is fixed. This means a lower stopping potential is needed to stop the electrons. On the following diagram, what is the energy needed to excite an electron from the ground state to the valence shell due to photon absorption? Pause the video now, unpause the video when you want to go through your answer. The valence state is the highest energy level, so that's energy level 4. So it is the difference from energy level 4, 9 eV, to the ground state, which is energy level 1, which is 2 eV, so the answer is 7 eV. On the diagram, what is the energy needed to excite an electron from shell 3 to shell 4 due to a colliding free electron? So pause the video now, then unpause the video when you want to go through your answer. It is 9 eV minus 6 eV, so it is 3 eV. On this diagram, what is the energy needed to ionize an electron from shell 2? So pause the video now, then unpause the video when you want to go through your answer. It would be the ionization level, 15, minus the energy from shell 2 for 11 eV or more, because anything above that will still cause ionization. On this diagram, what is the energy needed to ionize an electron from shell 3? So pause the video now, unpause the video when you want to go through your answer. It's 15 eV minus 6 eV, so there's 9 eV or more. On this diagram, what is the energy needed to excite an electron from shell 2 to shell 4 due to photon absorption? So pause the video now, then unpause the video when you want to go through your answer. It will be 9 eV minus 4 eV, and it must be exactly 5 eV for this to take place. For this atom, what would happen if a PD of 2 volts was passed through it, and why? So pause the video now, then unpause the video when you want to go through your answer. The current would dip as 2 eV would either cause an electron to be excited from level 1 to level 2 or from level 2 to level 3. This means that the kinetic energy of the electrons in the current will be lower as energy has gone from the electrons in the current to excite the electrons in the atom, so you get a dip in the value of current. For this atom, what will be observed with an ammeter if a PD of 13 volts was passed through it, and why? So pause the video now, then unpause the video when you want to go through your answer. Nothing would happen to the current as 13 eV will cause a ground state electron and all the other electrons to be ionized. This means that the kinetic energy of the electrons moving in the current would remain constant, so no difference would be observed. On this diagram, what are the possible energies which excite electrons without causing ionization? Pause the video now, then unpause the video when you want to go through your answer. From the ground state, you can excite the following energies: 2 eV, 4 eV, and 7 eV. From shell 2, you can excite the following energies: 2 eV and 5 eV. From shell 3, 3 eV. And from shell 4, there's no possible excitations that don't lead to ionization. From the following diagram, what is the energy needed to excite an electron from shell 2 to shell 3? Pause the video now, then unpause the video when you want to go through your answer. The answer is minus 8 eV minus 5 eV, leading to 3 eV, which is a positive value as the electron is moving to a less negative level. From the following diagram, what energies can be supplied to the atom to ionize it? So, pause the video now, then unpause the video when you want to go through your answer. The possible ionization energies are 15 eV or more, 8 eV or more, 5 eV or more, or 2 eV or more. From the following diagram, what energies can be supplied to excite the electrons from shell 3? So pause the video now, then unpause the video when you want to go through your answer. The only possible excitation from shell 3 is to shell 4, so therefore it's minus 5 minus 2 eV, which is 3 eV. From the following diagram, what energies can be supplied to excite the electrons from shell 2? So our electron can be excited from shell 2 to shell 3. So minus 8 minus minus 5 is 3 eV. And then from shell 2 to shell 4, minus 8 eV minus minus 2 eV, which is 6 eV. From the following diagram, what energies can be supplied to excite the electrons from shell 4? So pause the video now, then unpause the video when you want to go through your answer. There is no possible excitations from shell 4, only ionization is possible. From the following diagram, at what voltages would current dip if a current was passed through a gas of this atom? So pause the video now, then unpause the video when you want to go through your answer. Current dips when excitation occurs. So for energy level 1, excitation will occur at 7 volts, 10 volts and 13 volts. At shell 2, or energy level 2, it would be 3 volts and 6 volts. For energy level 3, excitation occurs at 3 volts. From the following diagram, what energies can be supplied to the atom to ionize it in joules? So pause the video now, then unpause the video when you want to go through your answer. The possible ionization energies are minus 2.4 times 10 to the minus 18 joules or more, minus 1.3 times 10 to the minus 18 joules or more, minus 8 times 10 to the minus 19 joules or more, and minus 3.2 times 10 to the minus 19 joules or more. So let's have a look at some questions regarding quantum physics. The first question says, a research team is testing different metal surfaces to optimize solar charging efficiency in a prototype space drone. They illuminate a clean metal surface in a vacuum with monochromatic UV light and measure the maximum kinetic energy of photoelectrons. The light used has a frequency of 1.15 times 10 to the 15 Hz, and the intensity is kept constant. The data below shows the results for the 3 different metals. Use the data for material A to estimate the work function of the metal in joules. Conclude whether this material will be suitable for use in a system where the threshold energy needs to be as low as possible. Determine whether the photon energy used in the experiment is sufficient to liberate electrons from material C. Then the engineer suggests that the increase in the intensity of the UV light could cause electrons to be emitted from material C. Evaluate this suggestion. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we know that E equals HF. So we pop in our values, we see it's 7.6245 times 10 to the minus 19 joules. We know 1.5 EV is 2.4 times 10 to the minus 19 joules. Therefore, we know the work function is HF minus KE. So it's going to be 7.62 times 10 to the minus 19 minus 2.4 times 10 to the minus 19, which is 5.22 times 10 to the minus 19 joules. So our work function is a moderate value, not the lowest, so not ideal where very low threshold energy is required, so another material could possibly be better. In our next one, we know E equals HF. Once again, that's 7.6245 times 10 to the minus 19 joules. Now, no photoelectrons are emitted when the photon energy is less than the work function. So this tells us that the work function must be greater than this value, 7.62 times 10 to the minus 19 joules. So therefore, a work function must be greater than 4.76 eV. So our photon energy is not sufficient, regardless of the intensity of the emission, also of the light being hit onto the metal surface. Finally, increasing the intensity increases the number of photons which hit the electrons per second, but not the energy per individual photon. If the photons still have energy below the work function, no electrons will be emitted from the surface. So the suggestion is incorrect. Frequency must increase, not intensity, to eject electrons from material C. An airport security company is developing a new sensor that relies on the photoelectric effect to detect high energy radiation emitted by hidden materials. The system uses a photoemitter surface and records the maximum kinetic energy of emitted electrons when exposed to radiation of varying frequencies. The graph below shows the experimental results for the sensor material. Use the graph to estimate the value of the Planck constant in SI units. Show your reasoning and comment on whether the results support the validity of the photoelectric equation. A security supervisor suggests that increasing the intensity of the incoming radiation at a frequency of 4.5 times 10 to the 14 Hz will cause electrons to be emitted. Suggest if the suggestion is valid or not. Finally, explain why this sensor would not function reliably when the visible light from a typical airport lighting. Suggest one practical design feature that could reduce the risk of false readings from ambient light sources. So, pause the video now, then unpause the video when you want to go through your answers. So, how do you answer this question? Well, in the first one, we've got to be aware that the gradient of the line is the Planck constant. So you would do 2.5 eV over 7.8 times 10 to the 14 minus 4.8 times 10 to the 14. So our answer is 8.33 times 10 to the minus 15 eV. We could then convert that into joules by times by 1.6 times 10 to the minus 19. So therefore, we get our answer to be 1.33 times 10 to the minus 33 joules. Now the result is reasonably close to the accepted value, so therefore it supports our quantum photoelectric equation. Next, what we can say is that the graph shows that the threshold frequency, which is the x-intercept, must be 4.8 times 10 to 14 Hz. So therefore radiation of 4.5 times 10 to 14 Hz is below the threshold. No emission occurs regardless of intensity. Increase in intensity will increase the number of photons, not their individual energy, so the suggestion is incorrect. Finally, visible light frequencies tend to be less than 7.5 times 10 to the 14 Hz. So the graph shows frequencies only greater than 4.8 times 10 to 14 Hz produces electrons. So this indicates to us that the visible light may be near the threshold, which could cause some false positives. So we could use a UV filter or shielding to block visible light, ensuring only the higher frequency radiation reaches the detector. A manufacturer is testing photocells that will be used in deep space telescopes to detect UV emissions from distant objects. In one test, monochromatic UV light of known frequency is shone on a clean metal surface in a vacuum. A variable potential difference is applied in the reverse direction to reduce the flow of photoelectrons. The current stops completely when the stopping potential is set to 1.80 volts. The frequency of the UV light is 9 times 10 to the 14 Hz. Calculate the work function of the metal in joules. Conclude whether this metal will be suitable for detecting lower frequency UV sources in space. A second experiment uses UV light of a slightly higher frequency, but the stopping potential remains the same. Discuss what this suggests about the energy the photoelectrons emitted and whether this result is expected. Suggest one possible reason why the stopping potential that was measured in A1.2 did not increase. Explain how an experimental or physical factor could have led to this outcome. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we know that EVS is equal to the kinetic energy, where Vs is 1.80, the stopping potential. So therefore our kinetic energy is 1.8 times by 1.6 times 10 to the minus 19. So it's 2.88 times 10 to the minus 19 joules. We know HF, we can work it through to be 5.97 times 10 to the minus 19 joules. Therefore, our work function is the two values subtracted from each other, which is 3.09 times 10 to the minus 19 joules. So again, it's a moderate work function, not ideal for low frequency UV, so it might actually miss some distant sources. Next, we know higher frequency means a higher photon energy, so normally it will expect a higher kinetic energy of the emitted photoelectrons. Now, the stopping potential is unchanged, which implies to us that the kinetic energy of the emitted photoelectrons has not increased. This suggests that the emitted electrons are losing energy before they are escaping. So this is unexpected in the ideal photoelectric conditions, so indicates that possibly that the electrons are colliding with something as they're leaving the metal surface. Now, one reason why it might not have took place as well is that there's surface contamination or oxidization, reducing the effective energy transfer. Or the detector might have a potential measurement error. The practical limitations or the surface effects may influence the results and not actually the photon energy. A company is designing an energy-efficient light source for a tropical fish aquarium. The engineers are experimenting with using a fluorescent discharge tube containing mercury vapor. Electrons accelerated through a potential difference of 11 volts collide with mercury atoms inside the tube. These collisions excite mercury atoms, which then emit UV photons as they de-excite. A phosphor coating inside the tube absorbs the UV and re-emits visible light. Calculate the maximum energy in joules that an electron gains from the 11 volt potential difference. Conclude whether this energy is sufficient to excite an electron in a mercury atom from the ground state to the first excited state. Some emitted photons have an energy of 4.9 eV, whilst others correspond to transitions from higher levels such as 6.7 eV and 10.2 eV to the ground state. Use this data to explain why a phosphor coating is required to make the tube produce visible light. An engineer suggests using argon instead of mercury because argon atoms emit photons at a single energy level of 1.8 eV. Evaluate whether this would be suitable for producing visible light without a phosphor coating. So pause the video now, then unpause the video and you want to go through your answer. Right, in our first one, we know that the value is equal to EV. So we convert our EV into joules. So we get 1.76 times 10 to the minus 18 joules. We then convert 4.9 EV into joules. So 7.84 times 10 to the minus 19 joules. 1.76 times 10 to the minus 18 is greater than 7.84 times 10 to the minus 19. So the energy is therefore sufficient to excite electrons to the 4.9 EV level. Next, we know that the 4.9 eV, 6.7 eV and 10.2 eV photons are emitted. We can work out the wavelengths for each one, 254 nanometers, 186 nanometers and 122 nanometers. All correspond to roughly UV wavelengths, which are invisible to the human eye. So a phosphor coating would be needed to absorb this UV and re-emit it in the visible range. Finally, we know E equals lambda over hc, so lambda is equal to 690 nanometers. Now 690 nanometers is in the visible red spectrum, so therefore it tells us that no UV is emitted, phosphor would not be needed. However, single energy emission would produce monochromatic red light, which probably wouldn't be suitable for illuminating an aquarium. Astronomers analysed the emission spectra of light passing through exoplanet atmospheres during transits across their parent stars. Specific emission lines suggest that which atoms are present. In one observation, a scientist detects a prominent spectral line at 121 nanometers and later observes additional weaker lines at 102 nanometers and 656 nanometers. The telescope's onboard database provides the following information about energy levels relative to the ground state in the hydrogen atom. Identify which energy level transitions could have produced each of the three spectral lines observed. Explain why the 121 nanometer line is the most intense, while the 102 and the 656 nanometer lines are weaker even though the transitions occur in the same atom. Then discuss the limitations of using visible light spectroscopy alone to determine the composition of distant planetary atmospheres. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, when we work it through by doing E equals hc over lambda, E will be approximately for 121 nanometers be 10.2 eV, for 102 nanometers be 12.1 eV, and for 656 nanometers 1.9 eV. So therefore 121 will correspond from n equals 2 to n equals 1, 102 will correspond to n equals 3 to n equals 1, and 656 corresponds from n equals 3 to n equals 2. Now the intensity depends on the probability of the transition and how populated each of the states are. Now most electrons will relax from N2 to N1, which will be the most common transition. Higher transitions like 3 to 1 are less populated, so there are fewer photons emitted. Now 656 comes from 3 to 2, a less frequent transition leading to weaker lines. Now, many key transitions fall outside the visible range. Now, in addition, atmospheric absorption and telescope sensors may limit the detection of non-visible light photons. So the visible light alone will give an incomplete data on the atmospheric composition of the exoplanet. A group of scientists is conducting an experiment using an electron diffraction tube. When electrons are fired at a thin layer of graphite, a circular diffraction pattern appears on the fluorescent screen. The team reduces the accelerating voltage applied to the electrons and observes that the spacing between the diffraction rings increases. They discuss whether this supports the idea that electrons behave like waves and whether this might influence our understanding on the nature of matter. Explain how the observed changes in the diffraction pattern provide evidence for the wave nature of electrons. Include in your answer a discussion of how the momentum of the electrons affects the pattern. Discuss how the idea of wave-particle duality has influenced the development of models of matter. Include reference to how scientific theories are reviewed and accepted by the wider scientific community. Evaluate why the demonstration of electron diffraction in a lab experiment is considered strong evidence for the quantum model of the electron rather than just a curious visual effect. So, pause the video now, then unpause the video when you want to go through your answer. In our first one, diffraction is a wave phenomena. The particles producing diffraction implies that it's wave behaviour. The larger ring spacing at lower voltages means that the electrons are diffracting more. A lower voltage gives a lower speed, which gives a lower momentum. From de Broglie's hypothesis, the lower momentum gives a larger wavelength. Now, therefore, this tells us that wavelength affects the diffraction pattern, which supports our wave-particle duality. Now, duality challenged classical physics and required new quantum models. It provided an explanation for phenomena like electron diffraction and the photoelectric effect. Now, theories must always undergo peer review and experimental validation. The wider spread acceptance followed repeated confirmations in independent experiments. Finally, the diffraction pattern is consistent and predictable. It's not a random effect. It can only be explained by electrons having a wavelength, supporting the quantum theory. So this confirms that matter exhibits wave behaviour. A team of engineers is testing a new electron microscope that relies on the electron diffraction to probe the structure of crystalline materials. The system allows fine control over the accelerating voltage, and the resultant diffraction pattern is measured on a detector screen. They record the distances between the central bright spot and the first diffraction ring, called the fringe radius, at various accelerating voltages. Describe and explain the trend in fringe radius as the accelerating voltage increases. One member of the team claims that the results prove that electrons are waves. Evaluate this claim using both the data and your understanding of quantum physics. The microscope is being marketed as capable of detecting features smaller than the wavelength of visible light. Assess whether this claim is realistic. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, as the voltage increases, the fringe radius decreases. The higher voltage means the electrons gain more kinetic energy, so are moving faster. The de Broglie wavelength, lambda equals h over mv, increasing velocity means shorter wavelength. The shorter wavelength means less diffraction, leading to a narrower ring pattern, and the trend is consistent with wave-like behaviour predicted by quantum mechanics. Now, the data shows predictable diffraction patterns, which is wave behaviour, but electrons also show particle behaviour, such as the photoelectric effect. So the result supports wave-particle duality, not that electrons are only waves. The claim is too simplistic. Evidence supports a dual nature, not a pure wave idea. Finally, as the voltage increases, the de Broglie wavelength decreases, so our resolution improves. The visible light wavelengths 400 to 700 nanometers, the electron wavelengths at these voltages are much shorter. So the claim is realistic. Short electron wavelengths will enable higher resolution imaging. So that brings an end to our revision session today. If we've been successful and we've learned in this revision session, we can answer A-level physics exam style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you for watching this video on particle physics, which is part of AQA A-level physics paper 1. Thank you so much and have a lovely day.